Hello again, folks, in 114. Today we're going to be covering section 6-9. That's the calendar. I always forget to do that. I didn't cross this out yesterday. Today is Wednesday, June 2nd, so we're going to be covering section 6-9. The packet that I have for you has a lot of pages. They're all, well, it's mostly just diagrams. Let's see, I made this yesterday. This is an overview of the types of equations that you're likely to see in MAT-114. It's really, at most, these three. You probably won't see too many of these, if any at all. But I figured they're worthy of mentioning. Always give somebody a little bit extra to show them that there's something beyond, you know. Show them where they came from, where they're going, you know, and what comes after them, all right? So please do print that if you're following along. I'll add some notes to it. This is a slightly older diagram. This is different methods for solving quadratic equations, all right? Typically, what we would do is basically the second procedure in tandem, these two things, or the quadratic formula, which I think everybody knows. And we have a tendency to kind of go to that automatically. The only thing about it is, although it works for everything, it's sometimes more trouble than it's worth because it's tedious. If you go about the process of solving a quadratic via factoring, here is an overview of different means of factoring. I made this extra page after this as a sort of order of operations, but order of factoring. This is what I do personally. For any size polynomial, you might try factoring out a GCF first. It's sort of undistributing. Right? For something that is 4 terms wide, or something that is 3 terms wide, you might try these, or 2, you know, and so forth. You're not really responsible for all of these, but it's an overview that I would follow. I did include an older sheet that you probably have. This is the rules of divisibility. Often you have to rely on this, you know, as sort of in the back of your head when you are factoring, when you're trying to decide what the monomial is factored out. This is sort of an idea of when you're factoring radicals. Bless you. The ideal is that you factor out the highest possible perfect square, if you're dealing with square roots, and then whatever the leftover is. Sometimes the leftover is a composite number like 6, but if you factored 6 further, it wouldn't be to your advantage, so you just sort of leave it like that. This is just something that's good to memorize. The square root of perfect squares, 1, 4, 9, 16, 25, these numbers in purple are perfect squares. If you took the square root of those, you would get a whole number as an answer. These are rational, they're not irrational. There's also some perfect cubes and perfect fourth roots. Less and less. Here's an example of a word problem, and that's that, all right? So let's start with this. I'm going to annotate a little bit, and we'll get going. Let me adjust the camera. Close my eyes here. And begin. It's not quite centered, so there we go. Okay, this is part of a diagram that I keep trying to refine depending upon the class that I'm teaching. For our purposes, it's really just essential to be limited to this half, and maybe this little cloud here. All right. Now, the types of equations that we have seen are the linear type. Right? And in a nutshell, you can tell that that's what you're working with, if you examine the variable's degree, right? Although it isn't written, right? If there isn't anything written next to x, you would have to assume it is 1. If it is 1, that makes it essentially of a linear type, right? And the procedures involved when you're trying to solve a linear equation, and sometimes this is just called first degree instead, are, you know, what you're familiar with, opposite operations. So if it says something like add, you're going to subtract, and if you multiply, you're going to divide. And in order to balance it, you do to both sides of the equals. Those rules, or procedures, whichever you prefer, will never go away, all right? Even if you try something more sophisticated, all right, you're eventually going to come back to this, all right? It is the foundational information, which is why it is so imperative that a person acclimate and internalize this, okay? So remember that, all right? How do you manipulate an equation to isolate a variable? You perform opposite operations and you balance. You do it to both sides to make it legal. Okay? So that foundational technique will be always part of some other problem. Okay? Now, if you up the ante just a little bit and you go to what would be a little bit more general, second degree equations that are polynomial based would be the quadratic type. Right? These are essentially synonymous. Usually when somebody is referring to quadratic, though, they're referring to something that has 3 terms. Right? But what you really need to zero in on, and that's the reason why I put this chunk of it without drawing the ellipses, is that the degree changes from being 1, which is not normally written, to degree 2. Right? So if you have degree 2, all right, realize that you will eventually perform opposite operations, do it to both sides for the sake of balancing, but there are newer sort of preliminary steps. All right. Now, what does that entail? A sneak preview, right? For our purposes, that usually means factoring and the zero product rule. Or it means the quadratic formula. There are others, and still there's a squaring technique. There is completing the square, which is where the quadratic formula originates from. Or in theory, you could graph something. If you pretend that the equation you're given is, instead of it being, say, equals 0, you say it equals y, and then you graph it, you can look for zeros. But that would really entail having either some graph paper on hand or a graphing calculator. Anyhow, it's really these two things: factoring techniques and the zero in tandem with the zero product rule, or maybe the quadratic formula. All right. Now, what makes something a polynomial-based equation? This is the building block. All right. You have your variable. Let's just assume it's x. And there are 2 key features. Usually people don't dwell upon it too much, but there's the coefficient, as always, and there is the exponent, which is sometimes just not obvious, but if it's not written, again, you assume it's 1. The condition for something to be polynomial is that the exponent has to be a non-negative integer. Non-negative integer is describing basically the other 2 possibilities of an integer, which is that in theory it could be 0, that's non-negative, or more likely a positive whole number, all right, is what would sit here,
all right? Hence 1, hence 2. If I didn't include it, but there could have been another category that is polynomial based, which would be cubic, you know, which would be degree 3, and so forth and so on, all right? This is a little bit more of a technicality as well. Most people don't dwell upon it, but the coefficient that is up in the front, it has to be real, which means not imaginary. And that just means you can't have the square root of a negative, say, something up in the front. All right, or the square root of an even index here. The root of an even root, I should say. A cube root would be fine for a negative, but a fourth root technically not. All right, it's really square roots though that you're more concerned about, and you're not even going to see this really because that's imaginary is really in the realm of maybe algebra 2 or more likely pre-calculus. Anyhow, just to show you sort of a pattern here of how things change, that's why I included this. The other types of equations, things that are essentially not polynomials, by definition, are the thing that kind of is a stack of them. Rational equations are not technically polynomials. You could say that they are basically a polynomial sitting on top of a polynomial in the style of a fraction. That is true. But if you examine the minutiae, all right, that is the degree, all right, they don't meet the requirement of being 0 or a positive whole number here. If you want something to be rational, the simplest example of an equation that's based upon this chunk, all right, it would be x to some negative integer. All right. So a negative whole number, essentially. This is actually an abbreviation as well. When you have a negative integer, you could alternatively write something as the whole thing in the denominator, and once you move it from its location to its opposite location, that is in this case from its top to its bottom, you write it as a positive, or you don't bother to even write the plus symbol. Right. Anyhow, you're not responsible for that, but that is technically what happens. All right. Then there's the situation, since we're considering basically whole numbers, positive or negative, where if you just change this other feature that you make this an actual fraction, the exponent, something like this, right? That is more or less an abbreviation for a square root, right? It's just that in the case of square roots especially, we don't bother to write the index number that would normally be sitting in this little check mark. We could, we just don't. And we don't normally write an exponent of 1. But if you wanted to translate from the rational style of the exponent to the radical style of the exponent, these two features would be situated here and here respectively. If you had 1/3, that would be a cube root. If you had 1/4, it would be a fourth root, and so forth. Again, you're not responsible for that, but you can see this is the train of thought. Whole numbers that are positive, all right? What happens when you make it negative? It represents that type of equation. Then this expression, respectively. What about if you change it to a fraction instead? It represents a radical, right? There's a logic to it, all right? Then there's absolute value equations, right? If you were to take the absolute value of a variable or some expression that's more complicated, what you end up having to do is to write two different equations without the symbol, all right? Anyhow, you're not responsible for that either. Right? What ends up happening is that you do this. You try to figure, you break this up into an equation, and then the second equation without the radical symbol, and then some positive number and some negative number, right? Remember, when you take an absolute value, it just considers the magnitude of something. The modulus lines here is what they call it, modulus symbol. All right, they ask you what is the magnitude is the outcome. In theory, it could start as a negative, right? In theory, it could start as a positive. But the end result in either case would be that you have the absolute value of anything would be just the magnitude. Anyhow, again, you're not responsible for that, you're responsible for this. For the sake of space, I did also include this up here. Equations, of course, are made from expressions. The halves of the equations are expressions, right? Now, you've probably heard these terms thrown around: monomial, binomial, and trinomial. What does that mean? Well, the most basic algebraic polynomial expression would be x degree 1, technically. I'm going to put a little parentheses around it to sort of encapsulate it for presentation purposes. Right. Maybe make it a little bit darker. You might want to put this over here, but I just didn't have space. A monomial looks something like that. A binomial would be, this is essentially one term. A binomial would be two term. A trinomial would be three terms. So something like x plus 2. Or if you have a trinomial, a lot of times it has it's quadratic, so x squared plus 2x plus 2. These are all polynomial expressions. They're just more specifically a mono, a bi, and a tri. All right, think about it as something with wheels. You know, a bicycle has two wheels. Well, a binomial has two parts, two terms. A trinomial, like a tricycle, has three parts. Beyond three, it would make sense, right? If you're keeping with that nomenclature, if you had a 4-term wide to call it, a quadrinomial, that would make complete sense. But the fact of the matter is that beyond 3, the math world has decided, just call it a polynomial in general. Just say 4-term polynomial. Anyhow, our focus for today is these type, right? The polynomials that are quadratic, and how we will go about the process of factoring them and then eventually solving them. You practice factoring first because it's one of the techniques for solving. Okay, so I'll put this aside a moment. This might be a better one. Let me switch slides now. And again, polynomial is a generalization. These are each specific examples of that. Here are the methods as an overview. If you already feel comfortable with the concept of a quadratic, and particularly if you feel comfortable with factoring, then you could probably go ahead and skip the conversation that follows, because I have to review that. It's the first time the subject of factoring has really come up in the course of this semester, or session, or whatever you want to call it. Anyhow, again, if a person had a graphing calculator, this is a fairly easy, efficient way of getting to the solution for x. All right. One interesting thing, when you have degree 2, expect 2 answers, even if it's, one is negative and one is positive. All right. In the case of graphing, you look for something called zeros, which is essentially the x-intercepts. Right. The solutions are known as zeros, which is another name for the x-intercepts. You just look at the x portion of of those ordered pairs. All right. What is more likely, for our purposes, is this process. All right. Factoring and then employing something called the zero product rule. All right. That means that you really need to have factoring down pat. All right. You could, if you want to, virtually every single time kind of jump the gun here and use the quadratic formula. Right? The quadratic formula happens to come from this process. It originates from the generalized form of a quadratic, ax squared plus bx plus c. Right? Rearranged in a particular way to solve for x, right, via this process of completing the square. The process of completing the square is the third method for solving, and it is useful, all right, but this is really pretty, you'd have to be pretty comfortable with the subject, all right, to do this, all right. I'm not trying to dissuade you from doing it. To me, it's like, it's probably just as much trouble as using the quadratic formula. So I would sort of limit the scope, or limit, my advice is pay attention to either factoring and zero product rule or quadratic formula. Squaring is pretty straightforward, all right? And if you have something that is being squared, like anything else, the opposite operation is what you would do. It's the opposite of squaring, square root, right? Just remember, when you take a square root, you get one positive and you get one negative result. Okay? Now, what I put in boxes here is pretty much how I go about the process of deciding which of these I'm going to use immediately. Like, for example, in the case of square root property, I would do that if I had this monomial on one side of equals. The term that has the variable x, if it's a monomial, then, and it's, degree 2, then go ahead and use the square root property immediately, and you don't need to do anything else. All right? If you had something that was basically a binomial on one side of equals, then you could, that would be a prime candidate for this technique of completing the square. All right? If you have a trinomial in either one of these cases, all right, a trinomial set equal to 0, a trinomial set equal to 0, which kind of implies that a person moved stuff around so that it was set equal to 0 strategically, then try factoring first, right? Because it usually is the fastest way to go about getting to the answer. And then take advantage of the zero product rule, right? The zero product rule is ascribing a name to something that you take for granted, and that is that 0 times anything is equal to 0, right? It'll make sense later. This arrangement of a trinomial set equal to 0 has a name. It's referred to as the standard form of a quadratic equation, which is what this thought cloud is referring to. Okay? If you're not given this, but you know you have 3 terms, you could try to arrange things via opposite operations so that it looks like that, all right? So that you can then factor. Alternatively, you could, if you have the same scenario where you have 3 terms set equal to 0, you could pluck out the coefficients and insert them in the quadratic formula, which I suspect that a student probably gravitates to doing that immediately just because it works 100% of the time. The only downside to it, again, is that, like completing the square, it's kind of swat and fly with a bazooka. All right. Anyhow, you have to be comfortable with the order of operations when you're doing something like this. If there's a mistake that students make 9 times out of 10, is they just didn't follow the order of operations. They put the numbers in where they're supposed to be, but they made an error because they didn't follow the order of operations. Right? Why the order of operations? Because if you're just dealing with the right side of an equation, you're dealing with an expression, so you have to follow the expression set of rules. Right? The guts of this, b squared minus 4ac in the formula, has a name as well. It's called the discriminant, and on upper level math, what it is used is to decide whether you're going to end up with a real solution or potentially an imaginary solution. Sometimes that happens. Right? I don't think you're going to see too many problems like that in this class, but in Algebra 2 you might. Okay, so of the techniques for solving a quadratic, probably we're going to be limiting ourselves to these 2. All right, which means we really got to nail this down. All right, factoring, which is another slide. Okay. Here's another oldie but a goodie. This is how factoring techniques would basically look. All right, I tried to give you a generalized form, A's and B's, you see here. But this is what you want to sort of mold things to look. You're going to start with some size polynomial, all right? And no matter what size it is, 2 terms, 3 or 4, all right, what you're going to try to do is factor it so that it looks like this. You're going to, it doesn't always work, all right? But you try this first no matter what. Only when it fails do you move on to maybe more sophisticated types, all right? What you want to do is draw parentheses and figure out what the common factor, ideally it's the greatest common factor, of each of the terms of the polynomial. What is the thing that they're all made of? And then write that on the outside. Now, as a technicality, that would be a monomial, because it's outside of parentheses. And it would be a GCF. It would be a greatest common factor. Different perspective, but it's referring to the same chunk. The leftovers on the inside would be, if you use the GCF, a simplified incarnation of the original polynomial. It would be a factored type, which just means that it's something times something else. Something inside, something outside. If this doesn't work, or even if it does work, eventually you might then choose one of these other types of factoring methods. Right? These two, which I couldn't think of how else to call it, but to sort of refer to it by what is going on. AC product pairs in tandem with factoring by grouping. This is kind of the go-to method. This is the thing that you do a lot, right? Sometimes it might seem superfluous, like, why am I doing this? I have an intuition and I could just get to the answer. I would never want to say to a student, deny your intuition, because that is a blessing. However, you have to be very careful when you're factoring that you don't sort of jump the gun, all right? And it's easy when you're factoring to sort of rely on intuition too much and not on strategy, all right? So if you want something that will work pretty well, 9 times out of 10, if you start with a trinomial, all right, what you might do is just pay attention to the coefficients up in the front and in the back, right? Together they form a product if you multiply them, all right? You would then compile a list of pairs of factors that make that product, right? And from that list, you would choose 2, all right, a pair that simultaneously, maybe if you add, maybe if you subtract, makes the middle term, all right? In essence, what you do is that you take a 3-term wide polynomial and make it 4 terms. And usually people say, well, that's crazy, I'm making it uglier, right? Why would I do that? The irony of the situation is that factoring something that is 4 terms wide allows you to just pay attention to 2 things at once rather than 3 things at once. All right, so it's actually easier to factor something that's 4 terms than it is something that's 3 terms. Go figure. And now we'll come back to that. All right. These are models that you would memorize, right? So I don't think they come up too often, but if you have something that is a perfect square trinomial, if it fits into this model, then it would factor this way. There's 2 incarnations of this, the one where there's a positive in between here and one where there's a minus in between here. And the effect is that you have identical binomial factors, but of the positive type or the negative type, which you can abbreviate further by squaring, if you like. If you have a 2-term wide polynomial, a binomial, where both of the terms are squares, exponent of 2, and sometimes that's obvious and sometimes it's not, then it might be the difference of 2 squares, right? As long as there's a minus in between. Another situation is where you have 2 cubes, and there's 2 incarnations of that as well. There's the positive incarnation and there's the minus incarnation. If you have a positive of 2 cubes, then it would factor this way. If you have a negative, all right, a minus, then it would factor this way. This is, I guess, the ultimate irony, because you start out with something so tiny and compact, right? And the way that it factors is that it's quite enormous. There's an acronym, a mnemonic device, for memorizing the sign configuration, which is SOAP. That's what I put here. Same as the original thing. So if it was positive, it's positive. Then the next sign would be opposite of that, whatever it is. And then the thing in the back is always positive. Same, opposite, always positive. same, opposite, always positive. All right, you're probably not going to see that too often, all right, in this class. Now, if something can't be factored, there's a word for that. It's prime. Just like there are prime numbers. Prime numbers are, you know, by definition, they have two factors, one and themselves, in which case you wouldn't bother to factor them usually. Right? Well, a polynomial that cannot be factored also uses that term, that phrase, that word, prime. Okay? We're probably going to be factoring in either of these two ways in this class. So our focus would be, when we get there, these two. Just got this blue. Okay. And again, just for a quick flash, if you get comfortable eventually, and it takes time, to decide what the proper order is to try factoring, this occurred to me as being the proper order. This is what I would do personally when I was factoring. And I decide based upon the size of the polynomial. All right? Any size, try the GCF first method. Monomial on the outside, simplified polynomial on the inside of a parentheses that you create. Right? You're factoring, you're breaking it into pieces. If you specifically have 4 terms, you try the technique that is in tandem with AC product pairs usually, unto itself, factoring by grouping, which is really just, again, it's putting the blinders on so that you only pay attention to 2 chunks at one time, 2 terms each. All right. 3-term polynomial, you might try the perfect square model, or you might try AC product pairs in tandem with factoring by grouping. Again, these 2 things together are very powerful. Right? Takes a little getting used to, but this is how I factor 9 times out of 10. Okay. If you have 2 terms, it might be the difference of 2 squares or the sum or difference of 2 cubes usually. If you have 4 terms, you might split into one monomial separated from the trie, and then try to factor the trinomial by itself. Right? If you have something that is higher degree, like degree 4, you're definitely not going to see that in this class, or it has established groups already, you might try something called U substitution. All right? Don't even worry about that. Okay. Let me do one example of this basic type first. I'll draw it up here. Okay. So we're going to factor this. (4x minus 8). Right? This is just an expression. Right? There's no equal sign because it's not part of an equation yet. We have to make sure that we're comfortable with factoring before we employ techniques for solving, which includes factoring. So we're just going to factor this. In fact, maybe I should just write it in a different color to give it some distinction. 4x minus 8. All right? This is a polynomial in general. All right? It happens to be a binomial, but we're not going to jump the gun. All right? We're going to try for any size polynomial, we're going to try to make it look like this. Here's an eyeball to remind you. All right, we're going to try to make it look like this. Something outside of a parentheses. And being that it happens to be 2 terms wide, 2 somethings on the inside of the parentheses. There's a minus here, we'll continue with that. All right. Now, how do we decide what goes outside first? The monomial GCF. Well, what you stare at is basically the coefficients, really, to begin with. Right? And consider the factors that make 4 and that make 8. In the case of 4 and 8, it's thankfully pretty finite. I'm going to write over here a little thought cloud. Things that make 4 are 1 and 4 and 2 and 2. Right? It's fairly limited, right? Things that make 8 are 1 and 8 and 2 and 4. I do them in pairs like that because it's useful. All right. If we're going to go for the GCF, all right, to put outside here, when you consider these factors of 4 and in tandem with these factors of 8, they always are going to include 1. Everything has a common factor of 1, even 0, right? But, all right, we want the greatest, that is the largest. So they're both even, they're both made of 2, but what is in fact the greatest choice here? It's 4 itself. So insofar as a digit is concerned, that would be extracted and put on the outside. And as an afterthought, you might look at the letters here. In this case, this has a letter and this doesn't have a letter. In general, I'll just put this here for now, right? When it comes to factoring variables, right? For a like letter, choose, somewhat ironically, the lowest degree. Right. So, for example, if this was x squared and this was x, you go with x to the first instead, because that's the most that they have in common. In this case, this does not have a letter, so we're not going to put a letter out here. All right. Now, you have to sort of ask yourself the question backwards. All right. If I factored this 4 out of the expression for x, what is it times 4 that makes 4? It would be, as far as the number is concerned, 1, which may or may not be superfluous. We may not have to write that if we don't want to. 4 times what would be 4x, x itself, all right? And usually if you can establish a letter in front here, the coefficient of 1, although it isn't wrong to write it, it becomes unnecessary because we have something to fill the void. Okay, then you continue, sort of thinking about it backwards. It's sort of undistributing. 4 times what is 8? It's 2. Okay. Now again, if you strategically choose the GCF, what should happen is that the guts here are simplified. I would get in the habit of trying to validate that suspicion as an afterthought if you had something worse than just this binomial, 4x minus 8, but this is in fact done, right? Right? You can't factor this any further. This is finished. All right? So this is a first example.
Let's do something more complicated.
Factoring, if you think about it, is sort of dividing without really consciously being aware of it.
Right. What I'm going to do is, I think I'm going to turn off my projector now, and we'll probably get into this, if not factoring, by grouping first.
Actually, the book, if you follow along in the textbook, they kind of do this a little bit out of order, so let me show you something. Put the lights on. All right. Factoring is essentially dividing without thinking. So what's the opposite of dividing? It's multiplying. All right. Now normally, again, I hate the way this book kind of toggles back and forth, but I'll just do it anyway. If you had to multiply binomial factors, you probably have some inkling as to how that is going to unfold. All right, here's an example. 2x minus 1, group they would usually, if you have a binomial, you have to isolate it as such, x plus 3. What you would apply is essentially the distributive property. Remember, the distributive property is telling you that you would have to multiply the outside thing times each of the inside things. All right. But in the case of a binomial, you can't just get away with doing that one time. You have to consider the other term that is in tandem here. So what you might do is draw a little range war again, this distributed to each of these things. But then remember that there's this other term, so you would have to do essentially the same process. Right? This process of combining things via multiplication is known as FOIL. Another acronym, another mnemonic device, right? It stands for firsts, outsides, insides, and lasts. Alright, meaning the first here and the first here. The things changing perspective slightly. The things on the outside, the 2x and the 3 are also outside. The things on the inside, the 1 and the x. The things that are the last. This is the last of this binomial, this 3 is the last of this binomial. Right. And the effect is, if you multiply, to remember, add the degrees of like letters. So for example, you could do the numbers portion of this first if you feel more comfortable. 2 times 1 is naturally 2. But if this is degree 1 and this is degree 1, add the degrees when you multiply them. So this would be x squared. Then it's 2 times 3, which would be a positive 6. And then it just happens to have this x here, so it's just 6x. And then negative 1 times 1x, or just x if you didn't bother to write that, would be minus 1x. And negative 1 times positive 3 is minus 3. What happens most of the time, or much of the time, is that the terms in the middle are like terms, remember. And legally speaking, you can add or you can subtract like terms. That would make it more concise, right? So as long as they're the same letter and technically the same degree, they are, alright, then you could subtract them in this case. Why subtraction? Because it's the combination of the signs here and here that dictate whether you add really or whether you subtract really. So one of each, subtract them. In which case you get a 5 for the digit with an x attached to it, and then you take the sign of the larger magnitude, that is distance from 0, which is a positive in this case. There happens to be this minus 3 sitting here, and there is this 2x squared sitting here. And that would be your answer for multiplying binomials. All right, now interestingly, there is another way you could do this if you're not really super comfortable with FOIL, so I'll just show you. Same problem. In the subject of genetics, there is something referred to as Punnett squares, which I believe is 2 n's and 2 t's, right? And it sort of looks like in the case of, pea plants or what have you, brown eyes and blue eyes. They have what looks like a window, right? There's a diagram, a simple diagram. What you could do is take the terms of the first binomial and sort of write them as a column heading here and here. And then take the terms of the second binomial and make them row headings here and here. So 2x, I'm going to just write along the top here, minus 1. And x plus 3, I'm going to write along the side here. And then you cross them and you write the solutions in the boxes here. So, same thing, this is really 2 times 1, so that would establish a digit of 2. and then x to the first degree times x to the first degree would be x squared. All right. X times minus 1 is minus 1 with an x attached to it. Positive 3 times 2x would be positive 6x, and negative 1 times positive 3 would be minus 3. And then what happens 9 times out of 10 is that the diagonal are the like terms that you would combine into 5. Right? It's just another way of thinking about it, borrowed from biology class. I always thought that was kind of neat. Okay, now, having done that, basically distributive property amped up to the next level, because it's rather than one term distributed, it's two terms. Let's go back to factoring, which again is dividing without really consciously thinking it. All right, since distributing is essentially multiplication, factoring being the opposite of that would be really dividing without consciously thinking about it. All right, so let's take a look at an example like that. Suppose that you had to factor this. X squared plus 6x plus 8. All right. Again, insofar as our methods are concerned, I would attempt to factor out a common monomial GCF, that is something outside of parentheses and some leftovers on the inside first. And if this fails, then move on to more sophisticated methods. Right? I think it will in this case, but let's verify. All right. I'm going to try, as I'm factoring, to essentially fill in this model. All right. A monomial GCF and some leftovers, for lack of a better expression. If it's a monomial, it has to be one term. If this happens to be a trinomial, and it is, then this would be 3 terms, right? Separated by pluses in theory. All right. If you examine the letters, right, they don't all have the same letter. All right, so I can't establish that as part of the GCF that I rip out of each one of them. Right? If I examine the coefficients, one of them is technically hidden. There's technically a 1 here. The factors of 1 would be just 1 itself. The factors of 6 would be 1 and 6 and 2 and 3. And the factors of 8 would be again 1 and 8 and 2 and 4. The only thing that they would have in common is, across all 3 of them, would be the factor of 1. Right? So if I were going to bother to put a 1 here as the thing that I extract from each one of these terms, that isn't going to change anything across the board. So it is unnecessary. All right? And therefore, first technique doesn't really help. All right, we move on to the more complicated techniques. All right, so what is the next model here? Well, you could jump the gun, all right? And I'm sort of reluctant to tell you that. So what I'm going to do is I'm going to try to confine myself to this space when I'm trying to explain the intricacies of what I really would encourage you to do. And then I'm going to show you what you can get away with over here. All right? What you can get away with over here is, instead of this model of something outside the binomial, the mono here, outside, and this inside, is you can try to up the ante and fill in this model. Something plus or minus something, and then a second one. So essentially, a binomial sitting next to a binomial. And in this case, they're both encapsulated in parentheses, as neither of them is outside. I think most people, whether they, have a word to describe the situation or not, probably do this intuitively. And the reason that I say that is in my own life, when I was in high school, right, this is the method of factoring that somehow got done to death. All right, they're like, here, take this trinomial and fit it in there, right? Just do it intuitively, you'll be fine. But that's not good advice, all right? It is great to have an intuition, but you should never just leave a kid to their own devices. Hey, good luck, kid. Here's a hammer, here's some nails, figure it out. That's just mean, all right? Don't do that, all right? Don't strand somebody in the middle of the ocean and give them a buoy and then say, you're okay. Help them. You gotta give them some structure. This is, again, if you have this as an intuition, keep it, all right? But just realize that there is maybe a better way to go about this when you have no idea how to factor, all right? So I'm gonna show you that now, what I consider a better idea. And the better idea for a problem like this is the second method. The second technique, which is AC product pairs in tandem with factoring by grouping. Okay, so that's a mouthful. It's unfortunate I don't have one word to summarize this as a technique. All right, so I'm really just describing it based upon how it looks. All right, now, the thing up in the front, the lead coefficient, assuming this is nicely conforming to the etiquette of descending order, that first coefficient you might call an A, as in an AC product. All right, the thing at the very back is a C. All right, this would be a B in between. Even if you were going to use quadratic formula, you would need to know that. All right, anyhow, we're going to take this A, and we're going to take this C, and we're going to merge them into an AC product, all right? And we're going to draw a little table here. The AC product, and then we're going to list some factor pairs. This works quite well. The only hard part, the only disadvantage would be if you don't know your multiplication tables well, or if you're not really comfortable with rules of divisibility, all right, which is why I included that diagram from a couple of sections ago. All right. Anyhow, forgive me, my allergies. What is 1 times 8? 8, right? All right, now, very easy. Let's list some pairs of factors, kind of like what I drew in a thought cloud here. The easiest pair. 1 and 8, right? I'll make a little separator here. I don't like the commas, even though I should put them. All right, that's the first pair. What's the second pair? I've used the next logical number, 2 and 4, all right? And there isn't anything else, really, to choose from. All right, now, these are things that multiply, because they're products, to make this number 8. If the thing that we're working with, I'm going to write it again over here. The thing in the middle is a 6. Let's take this thing in the middle, and based upon our choices established, let's factor this into a sum or a product. Let's zero in on that, don't pay attention to anything else. Of these choices, 1 and 8 and 2 and 4, separate from one another like so, which if you may be added or if you may be subtracted, would make a 6 of those two, right? These two. Why? Because if you subtracted 1 and 8, you get 7, which is not 6. And if you added 1 and 8, you get 9, which although it looks like 6 upside down, is not 6. All right, the only thing if you add would be 2 and 4. So I'm going to put a 2 here, I could put the 4 there first if I want, just be careful with signs. All right, and I'm gonna put the 4 there. Now, as an afterthought, I'm going to consider what the signs would have to be. You do have to remind yourself over here as well, right? What causes adding? Same signs. What causes subtraction? One of each. That's very useful to think of. If I want these two things, which are smaller than 6, to amplify, do I want them to add or do I want them to subtract? What makes things bigger also? Adding makes things bigger. So what causes adding? The same signs causes adding. So that means they either have to be both negatives or both positives. In this case, I want a positive outcome, so I'm going to make this a positive 4 and a positive 2. Now, as an afterthought also, I have to remind myself, you know, there's an x attached to this, so I'll just do that now. X here, X here. And what I will continue to do is I will now drag down this friend here, x squared, and this positive 8 over here. Now again, usually the very first time that you explain this to a student, they get frustrated and they throw a book at you because they go, hey jerk, you just took something that was 3 terms wide, which I could have went ahead and did that. All right. And instead you've overcomplicated it by making it 1, 2, 3, 4 terms wide. Jerk, failure, fire that man. All right. Why did I do that though? Because I'm not trying to teach you what the answer is to this particular problem. I'm trying to teach you a technique which will be invaluable to you when you can't guess. All right. So bear with me. Stick with me, my story gets better. All right. What we have done is we've applied the AC product here to establish these things, 2 and 4, to factor them, break them into a sum. All right. Why? Because now I can apply factoring by grouping, which you may have a little experience with, right? Again, the irony of factoring by grouping, it's something that you apply usually to a 4-term wide polynomial, which I've constructed. And the irony of it is that when you're actually trying to factor, you don't have to pay attention to but just 2 things at once. So in other words, your eyes can just pay attention to these 2 things now, not 3 things at once, ironically just 2 things at once. And you definitely know how to do that, all right? Because this thing, you could go back to the first technique now. Factor out a monomial GCF, and then some leftovers. It will just be shorter because now it's a binomial instead of a trinomial. Right? What is the obvious letter that these 2 things have in common? They have the letter X in common, so I'm going to write that on the outside of the parentheses. What is the number that they have in common? It would just be a 1, which is superfluous. All right. X times what would be x squared? It would just be another x, right? Because x degree 1 times x degree 1 would be x degree 2. X times what would be positive 2x? Would be plus 2. All right. That's halfway done. Now, here's the other thing. What you're hoping is going to happen when you factor by grouping is this. You want there to be a match in 2 binomials. And then you want there to be something left out. Right? This is more or less the ideal situation. Ideally, what's going to happen is you're going to hope that when you attempt to factor this chunk of this, again, you're just shifting your focus to just these 2 now. You're hoping that you get the same thing, x minus 2. And then there'll be some stuff on the outside of them in both cases. So let's do that. We'll get the monomial first. These do not have a letter in common. All right, so you can't put a letter here as the monomial on the outside. But if you examine the coefficient 4 and and this constant 8, what are they both made of? Ideally, the greatest common factor. They're all made of 1. Evens are made of 2. But in this particular case, what's the best choice? 4 itself. So therefore, the thing that you would rip out of each one of them and plop it on the outside would be a 4. And let's just borrow this sign here, and I'll put a plus there. All right. I always worry about signs as an afterthought. All right. I think that's a good habit. There's a plus here, put a plus here. All right. Now, again, when we figure out the guts that are left over here and here, 4 times what would be 4x? X. 4 times what would be 8? Plus 2. And exactly what I was hoping would happen, happened. There is the junk that is left over in here and in here. This is an exact match. And it has to be. If this is an exact match, then the way that this factors is like that. You write the match in its own parentheses. This is more or less the model here. The match is x plus 2. If even the sign was off, you may want to try to go back and tinker with it. Maybe you made a silly error. All right, but you put the match in one parentheses unto itself, x plus 2, and then this is my own sort of way of referring to it. You take the things that are on the left of each of these, and on the outside, so you might call them the left outs, you give them their own parentheses. So this would be x plus 4. And that is this factored. To make it a little bit easier to see, x plus 2, x plus 4. Now again, you might go, again, you are such a jerk, Ziegler, because, look how long it took you to do this, right? It takes me a long time to do anything because I have to, if I'm doing my job, all right, explain the minutia of what is going on here. If you're a teacher that does not explain details, then I'm sorry, you're not doing it right. All right, you really need to take the time. Now, sometimes people breathe down your neck and yell at you if you don't go fast enough, but all right, screw them, all right, because clarity is more important than anything else. People who don't have an attention span, they need to work on that. All right, anyhow, here, I will now show you the quick way to do this, only because if, again, you have the blessing of an intuition, I don't really want you to throw it away. All right, I just want you to realize that the techniques involved are more important than the individual answer to this problem. All right, so if you have this to factor, you already know what the answer is. It's x plus 2, x plus 4. All right, if you know from experience that most of the time, something like this, x squared plus 6x plus 8, will be a binomial times a binomial, good, you're ahead of the game. All right. What would probably sit in the front of each of these parentheses is to make x squared. Well, it would reasonably be x and x, right? If this is 8, what makes 8? Again, you have a couple of choices, though. You have 1 and 8, and you have 2 and 4. So you decide ultimately what sits here and here based upon what happens to be in the middle. And the larger and less warm, fuzzy, and familiar that this is, the harder it is to do that. So, in this case, because it's relatively easy, all right, you would reason to yourself, well, it would have to be 4, and it would have to be 2, because only when I add these, all right, would I produce a 6 simultaneously. Again, if you can take it from this to this, good, God bless you, all right? But just realize that for those problems where it would be a struggle for any person to get to this as an outcome, there is in fact a way to do that, all right? It just requires patience, all right? We need to cultivate, especially in America, all right, endurance, all right? This has been thrown out as part of our culture, and we need to reestablish it, all right? It's very important. All right, anyhow, the match gets its parentheses, for factoring by grouping, and the left outs get their parentheses for factoring by grouping, right? AC product pairs is really just for the sake of setting up a 4-term wide polynomial. All right, let's do maybe something a little bit harder. Yes, this is a better example. All right. Okay, if you had a factor, this is an example. Which is a better one? 6x squared minus 11x minus 10. Okay. Now, again, if a person were going, you should nonetheless, you tried the most basic method, first technique, and only when it fails do you move on to another. Mono GCF, and then some leftovers. 3 terms would be left over on the inside, right? Because it's a trinomial. Right. If you examine the letters, x, they don't all have x's, so you can't put that here. If you examine the coefficients, 6, 11, and 10, the GCF would be 1. All right, which if that were the case, all right, it wouldn't help you in diminishing or simplifying the original thing. So this first technique is not going to work immediately off the bat, all right? If you sort of jump the gun, all right, and you went, it's a trinomial, I know how to do this, and you get to here, plus or minus, a binomial sitting next to a binomial. It isn't impossible, all right, because you have relatively small numbers. This is a single-digit number. This is a small, it's the second out of the two of them. All right, double-digit number. So it isn't really impossible to go from here to here, but it isn't easy either, all right, because now it's double trouble. All right, you don't just have x up in the front here. You have a coefficient of a 6 up in the front. So that makes this a little bit harder, all right? Not impossible. So in this particular instance where you have something other than 1 here, I wouldn't do this at all, all right? What I'm gonna try once again is AC product pairs in tandem with factoring by grouping. And in order to accomplish that, I'm gonna make a little table to keep track. Factor pairs. All right. So, if this is sitting in the A position, and this is sitting in the C position, then that's my A and that's my C. Just take the digits, don't worry about the signs. All right. The product that they would form is 60, right? Now, what ends up happening, the larger this coefficient and this constant is, the more, potentially, the more factor choices we would have to establish here. So this can get a little tedious, which is another reason why, if, not to berate you, if you don't know your multiplication tables, make it your mission, all right? Especially as a teacher, because even if somebody denied you that, which is a tragedy, really, all right, to memorize them, all right? You can't let that propagate to the next generation. You have to fix it, right? Fix yourself and fix them. The reason why it is very good to know your multiplication tables by heart is exactly for this reason, because you have internalized a frame of reference, right, from which you could make predictions. If you deny a kid a frame of reference, you've hobbled them, right? It's terrible, right? So this is why I get very feisty sometimes, and I half kiddingly, All right, I say if your boss, all right, your vice principal, dean of students, or whoever, your principal, or the superintendent even turns around. If the president of the United States said to you tomorrow, don't make kids memorize stuff that's old-fashioned, blah blah blah, slap them right across the face for being stupid, because you need to have a foundational piece of knowledge, like the alphabet, in order to spell words. Don't ever deny somebody basic information, or even a basic technique. A kid who's 8 years old, they're not a scientist yet, all right? They got to get from here to there, all right? And you do that by, teaching the most basic technique to studying, which is memorizing things, all right? So I can't really stress that enough, all right? So, and you'll see why, all right? Here's a good system for establishing the factor pairs of 60. Start with the easiest one, all right? 1 and 60, all right? 1 times 60 is 60. Then, if you're a little rusty, right, go to a table of, you can get a multiplication table in the back of a notebook, if you have a notebook, a physical notebook, or some reference like this, and have the rules of divisibility on hand. All right, evens, right, which a 60 would be, are divisible by 2, which means they divide nicely, essentially. They're whole number factors. So 2 and then half of 60 would be 30. All right. The rule of divisibility for 3, which again is on that paper, is that if the sum of these digits is divisible by 3, then so is the whole thing. All right. I bet you probably knew that intuitively anyway. All right. So without having a phrase for it. All right. 3 times 20. All right. And we're continuing. Now, some things, admittedly, you don't need to even use, things that you've memorized, just things that you know. It's not really consciously memorizing. An hour is broken up into 60 minutes, right? How many quarters of an hour are there? 4. All right, so that is the 4 quarters of an hour that makes 60 times 15. That's a quarter of an hour, right? There's a way to often talk yourself through things. Right. Can't be afraid to try it, All right. This ends in a 0 or a 5, so it's definitely divisible by 5. So if you had to, rather than fall back on multiplication tables, divide by 5, all right? Because you know that you can. And you could use a calculator if you want to, but it's not too hard, right? The 5 goes into 60 one time with 1 left over, and 5 goes into 10 twice. So it's 5 times 12. Multiplication table of 12, also good to know. All right, and then you might wonder, geez, I've gotten pretty far here. How far should I go? Try to establish all of them. All right, and what you'll notice is, if you do this in a strategic way, is that if you start with the easiest, 1 and 60, these two things are as far apart as they can get. And as you proceed down this list, 1, 2, 3, 4, 5, or whatever the way that works, they get closer, the factors, and closer until you are right on top of each other, perhaps the same number, and you can't go any further. Then you're done, basically. So the next one might be familiar. You know that probably 6 times 10 is 60, right? I would try to remember to verify things. If you know your multiplication tables of 7 times 9 is 63, which is overshooting it. 7 times 8 is 56, which is too short. So it can't be 7. We just eliminated 8 and 9 in the process, all right? And then we've already gotten up to 10. So you're pretty much, this is the whole slew of choices. All right? Again, why is a person doing this? Because for the sake of factoring by grouping, which is ironically easier than what we have here, we need to take this original trinomial, 6x squared minus 11x minus 10, and break it, right? So we're going to break this middle term into, I'll put this in green perhaps, because it's fainter, all right? A sum or a difference using these choices, right? We multiply the established 60. we add or subtract to establish the middle term. So what possibly maybe adding, maybe subtracting makes 11. You get the satisfaction now at this point of eliminating choices, right? Even if it seems tedious, right? The mental exercise is what makes anything worthwhile, all right? Just like push-ups make you physically stronger. Struggling with something, as much as nobody likes pain, right? Mentally or physically, it's the struggle that makes you smarter, right? So don't ever think that it's a waste of time. It's not, all right? 1 plus 60 is way off. All right, so that's not going to work. If you subtract them, it's still way off. 59. 2 plus 30 is 32. 30 minus 2 is 28. That's not it. 3 added to 20 is 23, or 17 if you subtract them. Still not close enough. 4 plus 4 plus 15 is 19. If you subtracted them, that would be 11. Let's circle this because we should check the other two choices first. That's probably it, but we'll come back. All right, 5 and 12 is 17, not quite. If you subtracted them, you get 7, so it's not this. 6 and 10 is 16, and if you subtracted them is 4. So the only possibility is this. All right, incidentally, if when you're going through all of the trouble of doing this, and it ends up, no matter what you do, that you can't factor this, that just means one thing. It's not factorable, right? That sounds basic, right? But a lot of times a person, because they lack experience and a little panic-stricken, they'll go like, oh, I must have done something wrong. No, not necessarily. It could just be a prime thing. In this case, I don't think so. All right, anyhow, could be a prime polynomial, all right? It doesn't probably matter really where you put the 15 and the 4, but my intuition is that the 4 would be better closer to the 6 because they're evens, and this 15 would be better closer to this 10 because the 5 and 10, work well together, the common factor. They're both made of x, so this is going to be a 4x and a 15x. Now, we have to decide whether this is a sum or a difference really, all right? We need to know what the sign is here and here, all right? And in that case, we have to remind ourselves, all right? What causes addition? Same signs. What causes subtraction? One of each. And we decide whether we're adding or subtracting based upon the unique circumstances here. Now, this is a 15 and a 4, and this is an 11. So we need to, do we need to make this bigger or do we need to make this smaller? To go from here to here, what's happening? Shrinking or enlarging? I would argue that this is shrinking, right? At least the 15 is getting smaller. All right, so it's certainly not enlarging because that would be 19 if we added them, right? So this is subtraction, which means that we need one of each sign really, right? If the outcome is a negative overall, then we must, when we're choosing where to situate the negative portion of this one of each, we're going to attach it to the larger magnitude, right? And therefore this is a positive, right? Now the beauty of this is that we now just have to drag down 6x squared, and this minus 10, and yes, we have something that is arguably longer than what we had started with, right? But the advantage to that is we can apply factoring by grouping, which is just putting the blinders on. We only have to pay attention to 2 chunks at the same time. That's easier than 3, all right? So I'm gonna put a little dashed line down here so I don't get distracted. I'm like a horse, got the teeth for it, right? Anyhow, now we're going to go back to the first most basic technique by just paying attention here and here. What is the obvious letter in common? X, right? And since we have choices of x squared and technically x to the first degree, we choose the lower degree because that's the most that both of them would have in common. Of the things that are the coefficients 6 and 4, what is the GCF of 6 and 4? In this case, it would be 2. All right. And then to figure out what's left over here and here, we kind of think about it backwards. 2 times what is 6? 3. X times what is x squared? X. 2 times watt is 4. It's 2, and it would be a positive. And this x is already established, so we don't need to put another one there. All right, 2x times 2 is 4x. Right? What we're hoping when we shift focus here is, first of all, borrow this negative here. We're going to try to get the same guts here of the binomial. Right? When we have a match, everything is good. All right, so they don't have a letter in common, so I can't put that on the outside. But if you think of the things that make 15 and the things that make 10, what's the GCF of those two? Knowing your multiplication tables would tell you. All right, it is in fact a 5, or at least to help validate. Negative 5 times watt is negative 15x. The negative is sufficiently accounted for, so this would be 3x, it would have to be. So far, so good. Negative times watt would be negative 10. Positive 2. This is the one advantage to writing with markers. You can erase stuff midway in the conversation. Now, what we're hoping would happen did. Because the way that this is going to factor now is like so. The match is going to get its own parentheses. And what I just personally refer to as the left outs, they're going to get their own parentheses. Okay, so what evidently is the match? It is 3x plus 2. What are the things that are on the left of each of these and on the outsides as well? 2x minus 5. 3x plus 2, 2x minus 5. Again, if a person jumped the gun and attempted to go from this to the binomial factors, it isn't impossible if the numbers are relatively small, but it gets less and less possible the less and less familiar these numbers are that you're working with. In other words, things that are outside the realm of, even multiplication tables. It gets tricky, which is why having a system is very important, right? If you have the endurance, you will get to the answer. Another thing, what if this happened to be a prime trinomial? You really can't say for certain unless you try and fail in the middle of this process. Like for instance, if I got somewhere here and I did everything right up to this point, and no matter how I change the signs, it just won't factor, the end result is that these don't match, that means it's not factorable. And you could say with certitude, well, that's prime. But just guessing and going, I forgot it, it's prime, that's not really being rational, it's being emotional. Okay, so this is factoring. Let's try solving by factoring. Since that was really the essence of this entire day. We're going to finally solve by factoring. Now, as sort of a model here, what we want is this. If it's not given to you, you're going to purposely arrange the equation, which means there's an equal sign in here somewhere, to standard form. And standard form of a quadratic equation, never mind a function, they changed the nomenclature, the labeling, is this. Standard form looks like this. ax squared plus bx plus c is equal to 0, right? As long as we're talking about an equation, this is the proper labeling, right? You might get confused, and I wouldn't blame you because I have myself, right? There's the general form of a quadratic function, which looks remarkably similar to this. And then there's the standard form of quadratic functions. But when you just change this word from equation and functions, and yes, they are technically the same thing, but they have different jobs, different purposes. this is the favored way of referring to this shape, at least in the United States. Ax squared plus bx plus c equals 0. Think of that as being standard form, right? What is key here is this. Notice that it's set equal to 0, right? Which means that if the thing is given to not in that arrangement, move the parts around, right? All right, now the second thing is you're going to factor, right, by whatever means necessary. And then you're going to apply, something that is ascribing a name to something that you already take for granted, right? The zero product rule. What is the zero product rule, you ask? Right, it's this. What is, draw a little thought cloud. What is anything times 0? What's anything times 0? 0, right? Even if we don't know what this is. What is 0 times anything? Still 0, right? Even if I switch the position, it's multiplication, it's commutative, right? So it doesn't matter. And also, what is 0 times 0, right? Which is really unnecessary, but just to make it clear. 0 as well, right? Because that's anything, really. What if instead of writing the word anything, I have an algebraic expression written in here? Would that still be true? It would. Even if I shifted it over to here, right, in front, towards the right side of the multiplication, right, it would still be true, right? Even if it is this that's given to us, and we don't know what this is, something times something that happens to be equal to 0, then one could assume, well, either this is 0 by itself, or that is 0 by itself. It would have to be true. That's the zero product rule in a nutshell. Right? It's giving a name to something that you really already intuitively know. You know that 0 times something is 0. Right? It's great to be able to take advantage of that finally. Right? And here's how so. We're going to go through this process. Whatever is given to us, if it's not in this shape, we're going to make it look like that. If it isn't factored, we're going to factor it. All right, and it will still be equal to whatever the factor is. You might see your factors like that, you know. That, in our cases, will probably be the anything, or the algebraic expression times another one. They just won't put an x in between them. When two things are pressed up against each other like so, parentheses, parentheses, it implies that these two things are multiplied, hence their factors, right? And if they're equal to that, then we can take advantage of this. I need a little bit of space, so that's the strategy we're going for. Let me continue. All right. Let's start with this one. X squared minus 8x is equal to negative 15. This is for sure an equation, so we're going to appropriately solve. Now, being that it happens to be quadratic, we might employ factoring as the technique, right? this implies this. Right? So this implies this, solving, and this implies this, factoring technique. So how am I going to do that? I'm going to start by building a table, chopping up the thing down to equals here. If I want to get this to resemble ax squared plus bx plus c equals 0, then I need to, aka the standard form, then I have to essentially move 15. Right? How do I justify moving 15 from here over to here? Opposite operations, just like always. All right, so I'm going to add 15 in this case for the sake of cancellation. And since I don't really have anything to situate it underneath that matches as a like term, I'm just going to put it here temporarily. All right. The effect on purpose is cancellation. All right. Now, normally when I perform cancellation effect, or induce a cancellation effect, I don't bother to fill the void. But in this case, since this is an entire other side of the equation that is now left empty, and I want it to resemble that, I'm going to purposely fill the void, because it's practical in this case. Math people are notoriously lazy, efficient, all right, and they leave out zeros, ones, decimal points, and positive signs if it's a convenience to do so. But if it's not a convenience to do so, fill in the void, right? Now, to be a good guy, I'm also going to put this in descending order. So this is x squared. The next term would be minus 8x. And then there's this hanger on here plus 15 now. All right. It is this that now resembles the standard form that I'm going to attempt to factor. Now here, if you examine what you have to work with, x squared minus 8x plus 15. And there is no obvious coefficient up in the front here. I wouldn't blame you, all right, if you went for what is probably the way it's going to factor. All right, again, I would never want to talk somebody out of their intuition, because intuition in math world is a blessing. All right, just don't always rely on it, because it isn't always helpful. If you had a number here, like even just one digit higher, if you had 2, I wouldn't do this. All right. I would go through AC product pairs and factoring by grouping. For the sake of expediency, I'm going to just jump the gun myself here. I'm setting a bad example maybe, but I have the ability to toggle, all right, which is something that I want other people to have, all right? It comes on a case-by-case basis, all right? You know, after enough experience, all right, which is the best way to go, all right? The best gamble. So if this is x squared, what's probably going to sit here and here? X, right? If this is 15 and you consider things that make 15, it would be 1 and 15 and 3 and 5. It's fairly limited, right? Of those two pairs of choices, what probably is going to make 8? Right? Well, it would be 8. So 3 and 5. So 5 here, and let's just say 3 here. These need to amplify in order to enlarge to the magnitude of 8. So what causes things to get bigger? Adding. What causes adding? Same signs. All right. If this outcome is a negative, they both have to be negative. Same signs makes a bigger negative. A negative and a negative, when you add, makes a bigger negative. A negative times a negative is a positive. So that's the factored form of this, right? Now that's great, but at this point, this is factored. We're now going to get into the zero product rule to help us figure out what x is. The zero product rule says that, maybe this thing by itself is 0. Because 0 times whatever that is would still be the answer of 0. Simultaneously, maybe this is 0, right? Because even in spite of whatever that is, it would still be 0. So if that's the assumption that we can logically make, what we can do is we could write a teeny tiny little equation that involves just this chunk, all right, which is basically this. X minus 3 is 0, and a little teeny tiny chunk that involves just this half. X minus 5 equals 0. And what you see here as a result of that logic is that you have a very small algebraic equation that you can solve twice, right? Via the old methods of opposite operations, right? If I want to move this 3 from here to here for the sake of identifying x, or move this 5 from here to here, that is over equals, to identify this x, it's just opposite operations. It's the old techniques which never get thrown away. They get revisited. They're the foundational information. What is the opposite of subtracting 3? Adding 3 to balance. There is intentionally cancellation effect. So the x that's left over is equal to 3. That's one of two answers. Quadratics give you two answers. All right, always expect that. Same thing here. The opposite of subtracting 5 is to add 5. And then you add 5 here. And the outcome is x is equal to 5 in this case. Those are your answers. Now, you should be a good sport and test these two. All right. I won't do that just right now because there's a lot of other stuff to talk about. Oh, incidentally, the video that I recorded yesterday was like 2 hours. It wasn't the worst that I recorded. But it didn't, it was in processing hell for, for 12 hours. So finally I gave up at like section 6.1 and I just uploaded it again, like 1 o'clock in the morning, and somehow the second upload went better. So that should be available. Anyhow, it seems to me it is sometimes the day of the week that determines how long it stays in processing hell, and sometimes it's the length of the video itself. So like I've shot 4-hour videos, but as long as I did it on a Friday, it was okay. YouTube didn't have a problem with processing it. Anyhow. Let's see. All right. Let's get into the quadratic formula. And then we'll do a word problem and we'll be done. So now we're going to solve by quadratic formula. Quadratic formula. I'm squeaking it in there. Okay. Now, remember, even if you're going to go this route, you still want something to resemble the standard form, all right? So if you're not given something that is in this arrangement, make it look like that. What you're going to be extracting from it are the coefficients, A, B, and C, right? And whatever sign is immediately adjacent to them on each of the left. Okay, so be mindful of that. A lot of times people forget, they take the number, they don't take the sign. Okay. So here's a very good example for this. You really want to use this when something can't be factored. Factoring is still, that is to say, something is prime. Factoring is still the go-to method, really, right? And And I would kind of resist the temptation to always use this because it can get a little messy and maybe it's more trouble than it's worth. All right. If you have as an example this, 4x squared minus 8x is equal to -1. Let us note that this is not in standard form right off the bat, so we have to rearrange it a little bit. So again, draw a table, move the 1 from here to here. So if it says -1 to justify moving it, we're going to add. There's a cancellation effect, and we're going to purposely fill in the void. So this becomes 4x squared minus 8x plus 1. Because none of these are like terms, we can't really combine them. We could just sit them next to each other. Okay. Now, what is the a value? This 4. What is the b value? -8. Include that sign. What is the c value? It is now +1. Okay. The formula for quadratic formula is this. It is already arranged via the process of completing the square to look like this. It's minus b, sorry, plus or minus the square root of b squared minus 4ac over 2a. All right. Now, since your focus is going to be largely on the right side of equals, you must simplify this by order of operations. Right? Because technically you're just working with an expression, you're not working with an equation because it's already arranged equals this. Okay? What does that mean? It means that the guts basically here, the discriminant, it's kind of like something that is essentially in parentheses without really consciously seeing it that way, consciously thinking about it. This is what you must deal with first, the discriminant. Okay. All right, now you're just going to fit these values, 4, -8, and +1 in their respective places. I'm going to draw on top of them. Okay. But I'm going to make sure that I encapsulate them each also because they may have signs as an issue. For example, this b, there's a negative in the formula, right? But this happens to be -8 as a coefficient. So I'm going to do this, just to be careful. I'm going to tuck a little parentheses in here and make sure that I don't confuse the -8 that coincidentally happens to be here with what is in the formula. Same thing here. You want to make sure that you apply the square to not just the digit, but also the sign. Okay. In the case of a, the 4, you can get away with not doing that, but I would still make a little pocket for anything that I substitute. And then the c is just 1. Okay. Order of operations would dictate that I focus on this for a couple of reasons. Number one, even if there weren't parentheses here, I would have to pay attention to exponents second. Even though this is not written in the style of an exponent, a radical, that is a root, is the opposite of a square, all right? So it is of equal importance, just like division is the opposite of multiplication. So your focus must be here, logically, all right? Don't be ashamed. I do encourage this, please. Write the same thing over and over again redundantly with the little alterations that you make, because if you get, first of all, it's a fun sort of practice. You can see how things are evolving, and it makes it easier to avoid a mistake, which as a teacher, you know that you're not allowed to make mistakes, right? You know, people get mad at you if you even say something wrong. So be careful, right? Encouraging your students the idea of building an algorithm, that's really what's important. All right, so I'm going to evolve this slowly but surely. X is equal to a -8 here, plus or minus because it's a radical, and then we're going to look at the guts that are inside here. 2/4. All right. You have your choice between squaring an amped up form of multiplication, regular subtraction, or regular multiplication. You do this first, right? Squaring is saying that the thing that is being applied, all right, is going to be iterated. So it's -8 times -8. It's a negative times a negative, positive. What's 8 times 8? 64. All right. There's a minus here. I can get away, just for the sake of space here, with doing this multiplication before I write it again. All right. 4 times 4 is 16. 16 times 1 is just 16. So the second portion of this is that. All right. Now, what is the next step here? X is equal to, again, a negative, -8, technically plus or minus the square root of this inside guts of the radical, the discriminant here. This is just subtraction left over. What is 64 minus 16? It's not going to be great, all right? But if you took 10 off of it, it would be 54. If you took another 6 off of it, it would be 48, right? So this is going to reduce to 48. All right. Now, if you could, what you would want to do is attempt to simplify this according to radical rules. All right. So we're going to try to simplify. All right. It's never going to go away because it's irrational. But we don't have to just accept that it has such a large number. We could express the same irrational figure using smaller numbers. So we're going to, again, try to simplify. What's the process there? Well, without turning my projector on, let me just refer to the sheet here that I have. This is basically the strategy. We're going to try to break this up into 2 pieces, all right? In the first factor, which is still underneath a radical, we want to choose the highest perfect square possible, because we're talking about a square root here. And then that will leave us with maybe a prime number or perhaps a composite that would be not so convenient to factor further. Something like 6 is a classic example of a number that, although it isn't prime, you wouldn't bother continuing because it wouldn't make any headway. Now, I'm going to sort of leave this here, but I'm going to zero in on this portion of it and do the work here because I just don't have space. All right, to simplify. Okay, so if you're focusing for a moment on the square root of 48, all right, we're going to try to factor this ideally into the highest perfect square possible, and then there'll be some leftovers, for lack of a better phrase. Here, all right? That is basically simplifying something so that we're not using such a large figure 48. We have some smaller numbers that express the same amount. Again, this is a perfect example of an irrational number. An irrational number is an infinitely stretching decimal that it will never be a whole number, all right? How do I know that 48 is an irrational number? Because I've memorized the things that are around it, all right? What you see in purple here are perfect squares, right? And perfect squares, the square root of 1, produce a whole number as an answer. These produce a rational figure. These can be written in the style of a fraction, not an infinitely stretching decimal. They're wholes, all right? 1, 4, 6, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100 at least, all right? 48 is not on this list. It's between 49 and 36, right? So you would figure that the decimal would be 6 point something, whatever it is. We would have to, in this case, as before, consider the factors that make 48. Right? 1 and 48 is a pair of factors. Right? 2 and 24 is a pair of factors that make 48. 3 and 16. It's a 16, I swear. 4 and 12. 5 wouldn't work, but 6 would, according to rule of divisibility, and that is indeed 6 times 8. And let's see, what else? Anything else? 7 would be the next digit. And 7 times 7 is 49, so that's not it. We pretty much exhausted all the possibilities. Now, if you're wondering again, geez, dude, all right, how did you get all of these? It is a mixture of techniques. The logic of, I always know that I can start with the easiest one, 1 times the number. Then rules of divisibility for things that I just don't have memorized. So if it's an even, I know it has to be 2 times something. To figure out the something, divide by 2, it's half of it. All right, same thing for 3, all right? I didn't know the multiplication tables of 16, but I do know that this is divisible by 3 because 4 plus 8, according to the rule of divisibility for 3, divides nicely by 3, so therefore 48 would. And if that is the case, then it's 3 times something, divide by 16, 3, and get 16. 4 times 12, I happen to know. 6 times 8, I happen to know. All right, anyhow, that's the slew of possibilities to put here and here as factors. All right. 1 is the perfect square, right? It's in this list, right? 1 is a perfect square, all right? But, all right, it isn't necessarily the highest one, all right? What else is a perfect square? 4 is a perfect square. Again, it's not the highest one, all right? It isn't wrong if you choose that, but you may have to factor further, and then you end up recombining things. The highest perfect square in this case is 16. So that is the number that I would choose as the highest perfect square possible as one factor. And the leftover would be, its other factor would be 3. The thing that gets left behind. Now, here's what happens. If you consciously choose the highest perfect square possible out of these choices, this thing at least will escape the radical. What is the square root of 16? 4 times 4 makes that. So, a more concisely written version of the square root of 48 is 4 times the square root of 3. Right. And that's what would be fitted here moving forward. So, in the next line of part of this algorithm, you would have x is equal to negative 8, technically I shouldn't worry about yet, plus 4, I'll put it in red just to make it distinct, 4 square root of 3 in place of square root of 48 because it's simpler. It's simplified. And then this is sitting on top of 2 times 4. Okay. Now, just conforming as strictly as I can to the order of operations, I'm going to now, at this point, deal with this just sign combination. All right. Could you have gotten away with dealing with it earlier? Yeah. All right. But I'd be setting a bad example if I didn't wait until now. All right. So, to make a little bit of space, we continue. All right. This becomes, well, if you have, there's no number in between here, so the parentheses is really unnecessary. You can put a 1 if you'd like. This is a double negative. It is essentially 1 times the number here. All right, a negative times a negative is a positive. So this becomes regular ordinary 8. You can put the positive if you like. Right. Plus or minus, because radicals technically would have those two outcomes. 4 square root of 3 sitting on top of 2 times 4. Right? Now, if you can't really, you can actually simplify this before you even bother with this. So let's do that now. Right? you could factor, believe it or not, what you see sitting above this line, right? And again, the good rule of habit rule of thumb is, when you are dealing with essentially a rational expression, straighten out the top entirely, right? When you're following the order of operations, for a rational expression, which is what this technically is, right? Simplify the top, then simplify the bottom, right? Then, if it is possible, combine. Okay, so I'm going to stick with the idea of trying to simplify this if I can. All right. So I'm going to, ironically, perhaps factor. Pretend that this is an x for a second. If it was just 8 and then 4x, what is the common factor that makes both 4 and 8? It's 4 itself, right? So that means that I could factor out a 4, and then what would be left over for this 8? 4 times what would be 8? 2, all right? And then 4 times, well, plus or minus would be in between, all right? 4 times what would be 4x. It would just be an x if it was a letter. But in this case, it happens to be this square root of 3, really. So I'm just going to leave that like so. All right. What's the advantage of doing that? Well, what I have now is essentially a factored top. Right? And I have, technically, because I didn't bother to do the multiplication yet, I have, whether inadvertently or inadvertently, if that's a word, a factored bottom. So a kind of simplified top and a kind of simplified bottom, right? Which means, I'm just going to drag this up a little bit closer to it. This 2, which I didn't bother to introduce the 4 yet, all right, can simplify here and here. Right. So what you can get away with doing, or even better still, it would be a better choice to combine these. When you have something in factored form, which is when something is in parentheses for all intents and purposes. Maybe putting multiplication dots in between makes it a little bit more obvious. You can simplify the top and the bottom. That is, cross out stuff as if they were fractions, right? The denominators and the numerators. That essentially would reduce the 4 that happens to be here and the 4 that happens to be here. Right. What does that leave you with? It leaves you with this. It leaves you essentially on the bottom a 2. And on the top, the leftover guts of this parentheses, this factor, 2, plus or minus this, which you can still whittle away at. This is still what x is, right? This is as a summary, I don't feel like I can talk, a summary of what the solutions are. One situation you're adding, one situation you're subtracting. This is correct, all right, if you have them over a common denominator. If you want to make it look a little bit more concise, maybe a little bit more natural, I'm struggling to find a word, do this, all right? Separate them, all right? That gets a common denominator. that gets the common denominator. So what you would end up with is basically this now. You have x is equal to 2 sitting on top of 2 plus or minus, just to give this distinction, I'm going to use black, square root of 3 over 2. Right? Why bother to do that? Because you could take this to the nth degree. You can go one step further with at least this term. You can shrink it. It's a little bit of a glare here. So I'm going to get rid of that finally. Sorry for the delay in doing that. What is 2 divided by 2? 1. Right? Which means when all is said and done, this may be the slightest, and pardon me, the most concise way of summarizing what the solutions are. X is equal to the situation in which you add the square root of 3 over 2, or there's a comma I'm going to put here, the situation in which you subtract the square root of 3 over 2. Right. Because this is an irrational number, the square root of 3 is 1.7 something into infinity. Now imagine that divided in half, right? This is forever going to be irrational. It is better left in this simplified form. And you just leave the expression as being the sum of these two things or the difference of these two things. I admit it isn't very satisfying, but when you have things that don't factor, this is always going to be the case. Right? You're going to get stuck with something crappy. Right? If something was factorable to begin with, you wouldn't end up with irrational figures. All right? The whole purpose of the quadratic formula is really for that scenario. All right? Anyhow, it would be like adding half of 1.7, which is what? 7.5, pardon me, 0.75 added to 1, right? Or subtracting by 0.75, something like that, right? If it makes you feel more comfortable, do it, right? You can enter it into your calculator just to give you something of some satisfaction. All right, 1 plus, no, that's not right. The square root of 3 divided by 2. You might enter it like this in your calculator. Sorry for the glare. 1 plus, put a parentheses, the square root of 3 is encapsulated by itself, and then divide by 2, and you'll see what you get. You get 1.8 something into infinity. Again, an irrational number is never going away. That's the sucky thing about it. And so your figure for x would be approximately, 1.87, something like that. If instead you subtracted them, you'd have 1 minus the square root of 3 divided by 2. You might enter it like that. And now you see it subtracting. And you get that. Still a positive, thankfully, but still a terrible figure. All right, you get this. X is about equal to 0.13. 0.13, yes. Okay. All right. Rather than have a decimal that is a rounded number or infinitely stretching, which irrational numbers would be, it is arguably better to have this in a simplified form. Right? Which is why when you look at the answers, you're trying to confirm or deny what you got, maybe in the back of the book or whatever. All right, they often will just write them this way. And if not that way, they'll write them kind of doubled like this. at all reduced, you could in theory make that, like this. X is equal to 1 plus or minus the square root of 3/2. This is probably the most concise way to write it, because even that is the sum of the difference rather than separating them. Okay. All right. There's a lot to that, right, but don't be deterred. All right, let me get into this word problem, and then I'll stop. Because the word problem will involve, maybe a bunch of stuff at the same time here. Let me get a sip of water. Okay, here's our word problem. I probably didn't leave myself enough room. This is the whole thing. So let me just have that. I'll read it together and we'll try to pluck out some information before I get going. Red. All right. Dana and her husband recently, I have a friend named Dana. So Dana and Jim, recently installed an in-ground rectangular swimming pool measuring 40 feet by 30 feet. When you get a description to you and no drawing, do a simple drawing to summarize the information immediately. So what you can do is draw a rectangle. It doesn't have to be perfect, but something that basically looks like this. And give it its dimensions as described. It's longer this way and shorter this way. So 40 by 30, right? Feet and feet if you want to include that. They want to add a brick border of uniform width all the way around the pool, all sides of it. Uniform width is just simply saying that it never gets wider suddenly and then narrower suddenly. So I'll use red to encapsulate this. Just to keep it out of trouble, I'm going to put that 30 and 40 that I just wrote on the inside for those dimensions, like so. All right. The brick path, in theory, would be around it consistently the same width because it's uniform, like that. So I'm going to draw a slightly larger rectangle immediately around it. Reds would cooperate. All right. How wide can they make the brick border if they purchased enough brick to cover an area of 296 feet squared? This has to be an area because they use the phrase feet squared. This is a dud too. Put this over here. I'll test it later. What we're trying to figure out is how wide is this consistently all the way around it. Okay. I think that is as much information as we are going to glean from this. So what I'm going to do is I'll just kind of scoot this out of the way. You know what? I think I would be more comfortable if I just turned it off. All right. I got as much information as I need. All right, 296 square feet is the amount of brick that they have to work with. Put that over here and we'll thought cloud. 296 feet squared is the total available brick area. Alright, and that's pretty much as we need to know. Alright, now, if we're gonna figure out how wide this is, let's do this first. Right? Remind ourselves, what is the area formula? The area of a rectangle is equal to the length times the width. All right. This number, 296, is the total area that they have to work with. Right. So let's give that a name. Right. There is a red area. I'll just put in this extra information here. Complete, which by that what I'm implying is as if this was just the thing itself. Right? And then there's the pool area, which is blue. Which is just what would be in here. And then there is the donut area, for lack of a better phrase. The square donut, that is just the bricks. Okay, that would be the actual walkway that extends all the way around. I may have chosen better colors, but you get the idea as I shape this. And I think this is the end of this particular marker. All right, the brick donut, if you will, which is a squarish donut. That is officially a dud. Okay. I'm gonna have 8,000 greens because I never use them as always. Square donut, a cronut, or something like that. Yeah. Okay. The red area is a little bit harder to see because it really is something that you can imagine that extends all the way through everything. It's more or less the comprehensive, complete area. Right? So that would be the larger area. We don't know what this is yet. Right? The blue area we certainly do know. All right? The blue area would be what? It would be, again, it's just a pool. And since this is the formula for area, we could just multiply 40 times 30, right? Which would be how much? 4 times 3 would be 12. And then 12 with 2 extra zeros is 1,200 feet squared. Right? Save that number. If in theory, we want to get just the bricks in terms of an area, never mind the actual dimensions of the width of this, we'll get to that eventually. All right, what can we do with this known amount? This is the only thing so far that is known. All right. We could, in theory, subtract these two to get that. Because the square donut area that I've attempted to shade in black is just something that would be left over if you subtracted out the pool, right? This would be the leftover. And this essentially would be a total. A total area minus what is known would be equal to a leftover, essentially. All right. Now, as for describing the conditions here, all right, we can actually fill in a little bit because they did allude to this. The leftover area, otherwise known as just the bricks or the square donut, whatever way you want to refer to it, that we can replace with the total amount of bricks that we have as an area, which is 296 feet squared. This figure of 1,200 would therefore go here, feet squared. We need now to whittle this down. The total area. And in order to do that, I feel like I probably should just sort of draw my picture over again, but without the scribble. All right? I'll maybe do another incarnation of it, here, All right. This thing may be a little bit complicated because we're going to have to choose a letter to represent something, and it might be part of an ounce break expression. Don't be scared, all right? But whatever that equates to, I'm going to fit it in here, whatever this is. Okay? Now, humor me, because this is too sloppy to keep using it. So I'm going to draw it again, but without the mess. We do need to know this 1,200, and we are going to borrow that 296. But since we need to know some dimensions, all right, because we would need to know on a length and a width no matter what area we're calculating, and this is indeed an area, I'm going to fill in the dimensions that I do happen to know. All right? So from here to here is 40. And from here to here, which is parallel to it naturally, it's a rectangle, is also 40. Similarly, from here to here at least is 30. And from here to here is 30. Right. If this is in fact, if the brick patio, the brick walkway, how else are they referring to it? A sidewalk? Brick border, okay, is uniform, and it is, then pick a letter to refer to it. It would be logical, of course, to choose B, right? But I like X, so I hope you will humor me, all right? The X value would be something that is the same here all the way around as you go all the way up the sides and around this way. So from here to here would be the amount of X, right? And from here to here would still be the same amount of X, right? And also over here and there. X, X, and even as you turn the corner from here to here would be X. Again, you could use some other letter if you like. Okay, now, taking this, which is X, the amount of 40, and then X again, and just sort of sliding it down to superimpose here, this segment, and this segment, the entire distance would be x plus 40 plus x, right? Right. And similarly, if you were to take this dimension of x and then a 30 and then an x and just slide it over to here, it would be that long, and then this long, and then this long, which is the same thing as saying x plus 30 in this case, that's a plus I swear, plus x again, all the way from here to here. Okay, now, if you have two x's in sequence, either this dimension or this dimension, they're like terms, so if you wanted to make it a little bit less complicated, combine them. And in the case of red, a more concisely written way of writing x plus 40 plus x is to write it as 2x plus 40. Right. When you're considering this dimension this way, basically the same thing. A more concisely written way of writing x plus 30 plus x would be 2x. Right, but plus the dimension of 30. That is the width of the very largest, most completely filled in red rectangle. And this is the length of this dimension of this, again, completely filled in red all the way through rectangle. And what do you notice? They're a binomial times a binomial, which means we will have to FOIL it. We'll use Punnett squares if you like. Figure out what that total is, right? Combine it with this 1200. Manipulate it so that it combines with 296 eventually, all right? That's the setup, all right? We have everything that we need to know. Now, we've set the machine to go, now we gotta get it running. Okay, I need the space, unfortunately, so I'm going to erase a little bit. All right, if you FOIL this, 2x times 2x is 4x squared. 2x times 30 is 60x. All right, 40 times 2 is plus 40x. 40 times 30 is, what a coincidence, 1200. All right. Now, if before I introduce this to any of the other parts here, and there's this minus 1200 to be consistent in my color palette here. Let me simplify out what I can. And this would end up being what? 4x squared plus 100, then x attached to it, plus the 1200 that happens to be there. And now this is as simplified as that could get. 4 terms is now 3. The brackets that I chose arbitrarily to put in here, they're not necessary at all. There is coincidentally this 1200 here, and 296 on that side. What I can do is I can apparently eliminate these two because they're exactly the same amount. They like terms, they're both constants at 1200, which means that I now have this 4x squared plus 100 with an x attached to it, and free floating over here, which I'm just going to draw a little bit closer, is 296. All right. I have apparently something that is degree 2. All right. It's a binomial on this side right now, but I have another term over here, 296. If I want to attempt to factor this, without completing the square, because you could in theory go that route. I'm going to drag this 296 over to here and see what I can do. Right, how do I accomplish that? Well, make a table as always. This is a positive, subtract 296. It has nothing to double up with, so I'm just going to write it over here. Right? This is going to cancel again. I'm going to fill in the void with a 0 equals, and now I have 4x squared plus x 100x minus 296 equals 0. All right. Now, because this happens to resemble the standard form, you could, if you want to, use the quadratic formula. And I don't really want to talk you out of it because the numbers are so large to begin with. It would be trouble no matter what you do. All right. I'm going to try to set a good example nonetheless and attempt to factor it. All right. Now, how would I know to do that? Well, let me just remind you of one thing. That's old news. We always have our rules of divisibility. All right? Like the multiplication tables that we're taught to memorize, right? We have them as a frame of reference. So I know that 4 and 100 have a common factor of 4. I'm not so sure about 296, but if I verify with the rule of divisibility for 4 that says basically if the last 2 digits is divisible by 4, and it is, then the whole thing, 296, would indeed be divisible by 4. And what that means then is that you could rip a 4 out of each of these, right, and simplify it in the most basic way. Can't get a letter out of all of them because it's just these 2 that have x, but I can extract a 4 as a monomial GCF on the outside of this factor. Right, that leaves behind x squared. 100 divided by 4 would be 25 times 4 makes 100. And then this minus would be, let's see, 4 goes into 29 roughly 7 times, which is 28. The difference is 1. And 4 goes into 16 exactly 4 times. The only sucky thing that might happen here is that I get something that even after having factored it this much, I can't take it further. I'm suspicious of this negative here, quite frankly. All right. Don't be talked out of doing it, though. I made one boo-boo. Anyway, I think I made one little mistake. Let me just check. Which is why having the algorithm is better that you do. All right, my original terms were these. All right, I'm sorry. Before I continue attempting, because I'm a little suspicious, let me remind myself of what my factors were. I had 2x plus 30. And I had 2x plus 40, and then I attempted to FOIL them. All right, so 2x times 2x is indeed 4x squared. 2x times 40 is not, well, 2x times 40 is 80, right? This times this and this times this. 4x squared plus 80x. There's a boo-boo. Sorry. This is an 80. Okay. And then 30 times 2x is 60x. And then 30 times 40 is 120, so that's cool. The boo-boo is here, all right? This should have been, I'm sorry, 140, which means that I can't factor it quite this way, all right? 40. Okay. All right. So, because 140 is not divisible, well, maybe it is. Let me see. The last two digits would be divisible by 4, so it would be okay, but this figure here will change. Sorry. All right. 4 divided by itself would be 1. 140 divided by 4 would be 3, with 2 left over, which would be 35. Sorry, x instead. All right, and then 4 goes into the 7 times 1 left over is 74. All right, still that is suspicious looking. It is actually going to work. All right. Now, these are the correct figures. All right. 4 on the outside extracted from each of these in black. These are the leftovers for right now. What is this still equal to? This is equal to 0. All right. Now, what I have here, the leftovers, I'm going to try to do this too. I'm going to try AC product pairs in tandem with factoring by grouping. All right. Just what you see here. All right. I'm always a little suspicious when I have a negative on the end, but I think it will be okay. All right, we'll see. All right, as long as we can verify by doing it the brute force way, AC product pairs in tandem with factoring by grouping, because that's not brute force, it's strategic, but it's tedious. All right, I can confirm or deny any suspicions I have. So I need the space again. I'm gonna erase this. Okay. I have a 4 sitting on the outside here. I have this x squared plus 35x sitting here minus 74. And this is all set equal to 0. All right. If you want to, before we go ahead and factor this, you can actually divide this entire side by 4 here and by 4 here, and that will make it less ugly. That will reduce it to just what is encapsulated. X 35x minus 74 would still be equal to 0. 0 divided by 4 is 0. And now you could just zero in on this, pun intended. All right, now, over here, this is a 1, so that's our A. And this is C, this is 74. All right, so the AC product would be 1 times 74, which is just 74. The factor pairs, there might be many of them, but we'll run the gamut here. We start with the easiest. 1 and 74. It's an even, so it's got to be divisible by 2. 2 divided by, 74 divided by 2 goes into that roughly 3 times. 37 times, all right? I'll check the sum of the digits for 3, rule 3 for divisibility. All right, that would be 11, so it's not going to work because it doesn't work nicely with 3. 4, the last 2 digits, you have to just divide by 4 to check. 4 goes into this once with 3 left over. That would not be 32, it's 34, so that doesn't work. Doesn't end in a 5 or a 0. The rule for 6 is if 2 and 3 don't both work, then 6 doesn't work. 7 times 10 is 70, that's too short, and 7 times 11 is 77. 8 times 9 is 72, that's too short, and once you've gotten to 8 and 9, you're as close as you're going to get. These are the choices to choose from. All right. So what we will do is we will attempt to factor this middle term into either a sum or a difference using these choices. And from them you could tell that, well, these would probably work. All right. So I'm going to put 2 here with an x attached to it because it is an x, the brick width, and a 37 here, x. What would accomplish shrinking this? Subtraction would make these things, this at least smaller, to be 35. What causes subtraction is one of each sign. If I want this to be a positive outcome, the larger magnitude has to be positive, and the smaller thing would have to be negative. One of each causes subtraction, produces the 35, it becomes a positive because of the larger digit. Magnitude is positive. All right, now, coincidentally, what's sitting next to it? There's still this x squared sitting here, and there's still this minus 74 sitting here. Nearing the end. All right, now, remember, factoring by grouping, you just have to pay attention to 1/2 at a time, 2 things out of the 4. They both are made of an x, that would be outside parentheses. X times watt would be x squared, another x. X times watt would be negative 2x minus 2. What I'm therefore hoping when I attempt to factor these two onto themselves is that I get a match. So I want this to occur here. If it doesn't occur, if I don't get x minus 2 here, then that means it's probably not factorable, and therefore I'm going to have to use the quadratic formula. This is a way of confirming or denying that suspicion. Anyhow, of being prime. So I'm going to start with this being positive, because that's what's sitting here already. When I consider these 2 terms here, you can see that they don't have a letter x in common, but they might have some number in common. Right? That's a little bit harder to notice because the number 37 is not from the multiplication tables. All right, the closest you would get is 6 times 6 is 36. All right, and the number 74 is not too warm, fuzzy, and familiar either. The way that it turns out is that 37 times 2 is 74, right? So the GCF is, somewhat unexpectedly, is 37 itself. Now let's just make sure that the signs are all conducive here, all right? A positive 37 times watt would be itself, 37x, right? A positive 37 times watt would be a negative 74. Well, it would have to be a 2 because that's the way it works out. And the sign combination would have to be one of each when you're multiplying to produce a negative. A negative times a negative is a positive, but one of each produces a negative. So, lo and behold, all right, the junk that is sitting here and the junk that is sitting here is in fact an exact match, which is what you need it to be. When that occurs, it means it worked. It was factorable. It's not prime. So therefore, what we have as a factored form is this. The match gets written one time. The left outs, the things on the left and on the outside, x plus 37, they get their own factor, their own chamber. What is this all, meanwhile, set equal to? It's set equal to 0. So what we have at this point is something that we could apply the 0 product rule to. All right, the 0 product rule, again, is giving a name to something that you already know, that 0 times anything is 0. So just split the factors in 2 and pay attention to 2 at a time. This pair and that pair, respectively. Maybe this thing, x minus 2, is equal to 0. Maybe this thing, x plus 37, is equal to 0. If that's the case, we have a teeny tiny little one-step equation that we could solve. To move 2 from here to here would be involving adding 2. And that means that the x dimension, the width of the patio walkway, would be 2 feet. X equals 2. In this instance, I would have to move this 37 over to here minus subtraction, via subtraction. And look at what I get in this instance. That isn't bad arithmetic, but look what happens. X represents a real life width of a sidewalk. Can you, in real life, have a dimension that is actually negative? You can, all right? So there's, again, the difference between math world, where anything is possible, and the real world, where we have to conform the conditions here. Math world, you could have a negative dimension in geometry, I suppose. All right, there it is. All right, in real life, there's no such thing as a negative measurement. So what would you do? You'd rule this one out. Since quadratics, they produce 2 answers, right? That means that either one or the other is feasible. But if one of them is negative, right, in spite of the theory, you can't use it. So that's the dimension, right? The patio that we've been solving for in this brick that goes all the way around here, this pool, it reasonably is 2 feet all the way around it, the donut. That encompasses a lot, doesn't it? Anyhow, you see that I make boo-boos in the middle, all right? So don't feel bad, all right? It's the stick-to-itiveness that you have to encourage in your students, especially little kids. They give up very easily, all right? Don't let them, all right? The culture of Japan is that anybody can do anything, right? This much I know. I've never lived there, of course. But the cultural norm that we need to borrow and make the norm here is that anybody can do anything. That's true, right? We don't all believe that. We're not taught that in America, but we need to make it true. Right? We need to make it known, right? Why? Because any adult, including me, all right, can get through something if they just endure, all right? There's a method for everything, especially math, right? For homework, please do my lab section 6.9, right? All right. Thank you guys for sticking with me. We're almost at 3 hours, geez. All right. I'll see you tomorrow. All right. Be careful out there.